Welcome to G Fun Facts Online. Today we are tuning into a broadcast from the coldest, most remote places on Earth. We're not listening to radio waves, but to vibrations traveling through kilometers of solid ice. Deep within the vast frozen expanses of our planet's polar regions, a silent, powerful language is being spoken. It is a language of fractures, slips, and collisions, a narrative of immense change written in the rumbles and groans of Earth's ice giants. This is the world of glacial seismology, a science that is listening to glaciers to decode their secrets and, in turn, predict the future of our coastlines. For decades, our understanding of glaciers came from what we could see from above. Satellites gave us breathtaking images of the slow, majestic march of ice towards the sea. But that's like watching a blockbuster movie on mute. It doesn't capture the dynamic, often violent events happening within and beneath the ice, the very processes that are speeding up ice loss in our warming world. Glacial seismology offers a new frontier. By treating glaciers like living, breathing geological entities that generate their own seismic signals, or icequakes, scientists can now monitor a host of previously hidden activities in real time. Today, we'll explore this fascinating world, learn the vocabulary of these icequakes, and discover how this knowledge is sharpening our predictions of future sea level rise. Let's start by learning the language of the ice. Just as geologists study earthquakes to understand the stresses within the Earth's crust, glacial seismologists analyze a diverse range of seismic signals to diagnose the health of a glacier. Each type of event has a distinct seismic fingerprint, allowing scientists to identify what's happening deep inside. The most famous of these signals are icequakes, which are literally earthquakes that occur within the ice itself. They are generated when ice under immense stress fails and fractures. This can range from tiny, high-frequency pops to massive, low-frequency rumbles that can be detected thousands of kilometers away. One of the most common sources of icequakes is crevasse formation. As a glacier flows and stretches, stress builds up in its upper layers. When that stress becomes too much, the ice cracks, creating deep crevasses. This rapid fracture releases a burst of seismic energy. Sometimes, this process gets a push from meltwater that fills existing cracks, a process called hydrofracturing, which wedges the crack open. By mapping the location and frequency of these icequakes, scientists can pinpoint areas of high strain within a glacier and see how it's responding to changes in flow and melt. But not all seismic signals are sudden shocks. Sometimes, the ice produces a continuous, low-frequency vibration that can last for hours or even days. This is known as glacial tremor. This persistent hum is often the sound of a hidden world, the plumbing system of a glacier. As surface meltwater drains through giant vertical shafts called moulins, it creates a complex network of tunnels deep within the ice. The rushing, turbulent water in these channels generates a steady seismic hum. Scientists have found a direct link between the intensity of this moulin tremor and the water level in the moulins, giving them a novel way to monitor the daily and seasonal cycles of glacial melt. It's like having a stethoscope on the glacier's circulatory system. Then there are the most spectacular and loudest events of all: iceberg calving. When a massive chunk of ice breaks off a glacier's edge, it releases an immense amount of energy, generating powerful, low-frequency seismic waves that are dubbed glacial earthquakes. These can have magnitudes up to 5 on the Richter scale and are a direct measure of large-scale ice loss. The seismic signature of a calving event is surprisingly complex. The initial crack is relatively quiet. The real seismic power comes from what happens next. As the colossal iceberg, sometimes the size of a city, capsizes and overturns, it scrapes against the fjord floor and the glacier face, and its immense bulk displaces vast quantities of water. This entire chaotic process generates a long-lasting, low-frequency seismic roar that travels around the globe. By analyzing these signals, scientists can estimate the amount of ice shed, providing a way to calculate ice discharge from seismic data alone. Finally, there is the seismicity from the very bottom of the glacier, at the interface between the ice and the rock. This is called basal seismicity, and it's crucial for understanding the speed of ice flow. One of the most fascinating types of basal events is stick-slip motion. In some glaciers, the base can get stuck on a sticky spot on the bedrock. Strain builds and builds in the ice until it's suddenly released in a rapid slip event, almost identical to how tectonic earthquakes work. These stick-slip events can be incredibly powerful. At the Whillans Ice stream in Antarctica, for example, they occur with remarkable regularity, paced by the ocean tides, and release energy equivalent to a magnitude 7 earthquake. To capture these faint whispers and powerful roars, scientists deploy a sophisticated toolkit. The workhorse is the seismometer, an instrument that records ground motion. But deploying them on a moving melting glacier is a unique challenge. They are often buried in shallow pits in the snow or drilled into deeper, more stable ice to protect them from the elements and ensure a good connection. Everything has to be cold-rated and powered by batteries and solar panels, especially through the long, dark polar winter. To get a complete picture, scientists deploy these instruments in networks. One of the most ambitious is the Greenland Ice Sheet Monitoring Network, or GLISN. It consists of 33 seismic stations spread across Greenland, providing a continuous, real-time data stream that allows scientists to track the increasing frequency of glacial earthquakes and study the forces driving ice loss. But technology is always advancing. A promising new technique is fiber optic sensing. A standard fiber optic cable can be transformed into a dense array of thousands of seismic sensors. These are cheaper to deploy and can provide an unprecedented level of detail. Scientists are also applying machine learning and AI to the vast data sets. These algorithms can automatically detect and classify different types of seismic events, freeing up scientists from the tedious task of sifting through thousands of seismograms manually. This brings us to some incredible case studies. Let's start with Jakobshavn Isbræ in Greenland. It's the island's largest and fastest-moving glacier, a major contributor to sea level rise. Seismic monitoring has provided stunning insights into its behavior. Using the GLISN network, scientists studied the powerful glacial earthquakes from its terminus. By combining seismic data with time-lapse photography, they found that the most powerful signals weren't from the initial crack, but from the iceberg overturning and scraping the seafloor. They also discovered a more subtle signal: long-duration glacial rumblings. These events, lasting up to 40 minutes, are thought to be the collapse of large ice masses upstream, representing a previously unaccounted-for form of ice loss. Now let's travel south to the Pine Island Glacier in Antarctica, another of the world's most rapidly changing glaciers. Scientists were concerned about a massive rift forming in its floating ice shelf. A network of seismometers deployed on the ice shelf allowed them to track the rift's propagation in real time. They recorded the first ever seismic signal of a large-scale rapid rift propagation in Antarctica, discovering that a 10-kilometer section opened up at a staggering 35 meters per second, the fastest known ice fracture at this scale. Perhaps the most mind-bending example is the Whillans Ice stream in West Antarctica. Unlike most glaciers that flow steadily, the Whillans Ice stream moves in a series of dramatic, twice-daily lurches, a process known as stick-slip motion. These events are so powerful they generate seismic waves equivalent to a magnitude 7 earthquake, detected by seismometers around the world. It's a natural laboratory for studying earthquake physics. Scientists found that these ice stream earthquakes often begin with a period of slow precursory slip before the main rupture, a discovery that has major implications for understanding tectonic earthquakes. And in one of the most surprising discoveries, scientists monitoring the Ross Ice Shelf, the largest in Antarctica, found that it is constantly singing a haunting, dissonant tune. A dense network of seismic sensors revealed that winds blowing across the vast, snow-covered expanse caused the surface layers of compacted snow to vibrate, producing a steady hum of seismic energy. Even more remarkably, the pitch of this hum changes in response to weather. When storms rearrange snow dunes, or when the air temperature shifts, the frequency of the vibrations changes. This provides an incredible, near real-time method for monitoring conditions on the ice shelf, acting as an early warning system for the onset of melting. So what is the ultimate goal of all this listening? It's not just to understand how glaciers work, but to use that knowledge to improve our predictions of future sea level rise. The ice sheets of Greenland and Antarctica hold enough water to raise global sea levels by tens of meters. Even a small increase in the rate of ice loss could have devastating consequences for coastal communities. The complex computer simulations used to project sea level rise, known as ice sheet models, have always been hampered by uncertainties. They struggle to accurately represent processes like calving and the friction at the glacier's base. This is where glacial seismology provides the missing link. By providing direct observations of these previously hidden processes, seismic data can be used to calibrate and validate these models, reducing the uncertainty in their projections. Data on the frequency and magnitude of glacial earthquakes helps develop more realistic calving laws for the models. Seismic observations of basal slip and tremor help constrain the friction between a glacier and its bed. This provides a much more accurate picture of ice loss and, in a broader sense, gives us an early warning system. The increasing frequency of glacial earthquakes in Greenland is a clear signal that the ice sheet is responding to rising temperatures. The subtle changes in the seismic hum of the Ross ice shelf may be a harbinger of future instability. By continuing to listen to the silent roar of the world's ice giants, scientists are not only deciphering a complex and alien language, but they are also providing the critical information we need to prepare for the profound changes coming to our planet. The faint tremors emanating from the polar regions are a stark reminder of the immense power of these frozen landscapes and of the urgent need to understand and protect them. Thanks for tuning in to G Fun Facts Online.